In this video, we will solve some examples on Hamilton's principle. Our first problem is deduce Newton's second law of motion from the Hamilton's principle. Here, we have to obtain Newton's law of motion from the Hamilton principle. For that, suppose the particle of mass m be moving under the action of conservative forces F. If r bar is a position vector of the particle, then kinetic energy T is given by T equal to 1 by 2 m r dot square, while the force F is equal to minus dou V by dou T, dou R. Force F is given by minus dou V by dou R. From this, we can obtain delta V equal to minus F into delta R. Using these values in Hamilton's principle, we get integration from T0 to T1 of m r dot delta r dot plus f dr dt equal to 0. Integrating the time derivative, and delta variation we get m r dot delta r from T0 to T1 minus integration from T0 to T1 m r double dot minus f into delta r dt equal to 0. This is the first equation. Since the endpoints are fixed, there is no variation at the end point. Hence, the equation 1 becomes integration from T0 to T1 m r double dot minus f into delta r dt equal to 0. This equation is true for every virtual displacement delta r, and hence the integrand must vanish. This proves that F equal to m r double dot, which is a Newton's second law of motion. Our our second problem is a particle moves on a smooth surface under the gravity. Use Hamilton's principle to find the equation of motion. Here, for solving this problem, let x, y, z be the coordinate of a particle at some instant moving on a smooth surface under gravity. If z is the vertical, then kinetic energy and potential energy of the particle are T equal to 1 by 2 m into x dot square plus y dot square plus z dot square and v equal to mgz. Hence, the Lagrangian of the particle becomes L equal to 1 by 2 m into x dot square plus y dot square plus z dot square minus mgz. The Hamilton's principle yield integral from T0 to T0 to T1 of m into x dot delta x dot plus y dot delta y dot plus z dot delta z dot minus mgz into dt is 0. Since delta of d by dt is nothing but d by dt of delta, we can write above equation as integration from T0 to T1 m x dot d by dt of delta x plus y dot d by dt of delta y plus z dot d by dt of delta z minus mg delta z equal to 0. Here mg delta z dt equal to 0. Integrating the first three terms by parts. These three terms we shall integrate by parts. We will get m into x dot delta x from t0 to t1 plus m into y dot delta y from t0 to t1 plus m z dot delta z from t0 to t1 minus integration from t0 to t1 of m x double dot delta x plus y double dot delta y plus z double dot delta z plus g delta z into dt equal to 0. As coordinates of the endpoints are fixed, delta x from t0 to t1 equal to 0, delta y from t0 to t1 equal to 0, delta z from t0 to t1 equal to 0, and hence all these three terms vanishes and the equation becomes integration from t0 to t1 m into x double dot delta x plus y double dot delta y plus z double dot delta z plus g delta z dt equal to 0. Since delta x, delta y and delta z are independent, we must have x double dot equal to 0, y double dot equal to 0, z double dot equal to minus g, which are the equations of motion of the particle. Thank you.